Welcome everyone. I'm very happy to kick off the technical sessions at WOOT today with our work on security through transparency, tales from the RP2350 Hacking Challenge. This is joint work between a lot of different people, me, Aedan, Kévin, Tom, and also Andrew over here. I will give a little bit of context how this collaboration started later in this talk. So what will this talk will be about? First, I'll set the context, like what's going on, what is the RP2350 challenge, why do we need a paper about it? Second, I'll talk about the RP2350 security features, going on with the different attacks we found, and kind of recap the lessons learned or reflect what we think was cool about all of this. So let's get started with the context. Last year in August, Raspberry Pi released the RP2350. The successor to the widely successful RP2040. So if you know the Raspberry Pi Pico boards, the Pico 2 is powered by the RP2350. Alongside the release of the chip, Raspberry came to DEF CON and said like, hey, community, please hack our stuff, hack our chips. We designed a hacking challenge for you, and can you have a look and try to break our secure bootloader and our secure boot chain on our devices. I was told they were afraid that at DEF CON, where they released it, that maybe someone comes in already like just 1 or 2 days after they released the challenge and said like, yeah, I broke it, but luckily that was not the case. So there is some nice security features going on, and eventually the challenge ran until December of last year, and in early January, the winners were announced. There were 4 winners to this challenge and 5 entries discussed in the blog post by Raspberry. And that's how we end up with 5 authors on this paper. Each of us had one of these entries which were nominated by Raspberry of being a qualified entry to break their secure boot, or to break their security of their chip. So let's look a little bit at this chip, the RP2350. Released in August last year, dual-core MCU meant for low-level embedded processing. What I find really neat and interesting that it does not only have 2 cores, but each core can also run in one of 2 instruction set architectures. So they do embed both an ARM Cortex M33 core and a Hazard 3 RISC-V core. Now, of course, they cannot run at the same time, but only one of these different ISAs is active at the time. It also embeds the secure bootloader, which has some nice fault injection hardening we will talk about, and the bootloader itself is designed to run on the ARM core, or the secure bootloader. Now, why are we talking about security through transparency, or what's the transparency aspect to all of this? It's Raspberry Pi has been really open about their chip. They have extensive documentation, like this manual. That's the old revision. It has 1,357 pages. The new one, I think, is at 1,380 pages, so some additions. Everything is very well documented. Same with the boot ROM. The boot ROM is not only available in source code, but also with build artifacts, with ELF files. So one can match a low-level binary code with the source code, which was able to generate it, with all of the different revisions which were developed by Raspberry Pi. And same goes for the hacking challenge itself. It was put on GitHub with all the description of what has been done in which way, and the source code for how the challenge is set up. Now, before talking more about what this challenge does, we need to recap very quickly the different security features which the RP2350 provides us. In a nutshell, I think there are 5 relevant security features. First, the general Cortex M33 security features. Most importantly, the Cortex M33 implements Trust Zone M, so we have a secure and a non-secure world, which is heavily used by the bootloader. Then it has one-time programmable memory, a glitch detector, redundancy coprocessor, and the secure boot chain, which we all get into more detail now. So the runtime programmable memory, or OTP memory, is implemented as anti-fuse memory, and it configures all the critical components of the boot and of the chip itself. It says which core and which instruction architectures are enabled, whether debug access is on and off, whether the glitch detectors are on which sensitivity level. It's also relied upon during secure boot. It stores the key material for signed firmware, like the public key material. And it also allows locking of one-time programmable memory page. So once you set a security critical information bit, you can lock the OTP page, leading to that only in certain permission settings the contents can be read. We will get to that a bit later. Second noteworthy security feature, or third, is the glitch detector. The glitch detector, in a nutshell, operates by using 2D flip-flops, which at different point in time during one clock cycle sample the power line, or the power domain. Under normal operation, this should always be the same, right? Like a chip always consumes power, there shouldn't be too much. However, if you start experimenting with fault injection, EMFI, voltage fault injection, similar, you suddenly will see differences in the power domain between those 2D flip-flops, and the chip will just reboot, the glitch detector would have been triggered and said, hey, there was something funky, please double check what's going on. Another security feature is the redundancy coprocessor. So the redundancy coprocessor does a full bunch of different things. It provides stack canaries from hardware with a pair random seed. This is meant to mitigate ROP attacks or similar in the bootloader. It provides instruction delays. So with certain coprocessor accesses, there would be a random timed instruction delay between 0 to 127 clock cycles. So if you go for fault injection attacks, you would have to deal with some randomness. Then it has some sequence count checking, so it makes sure that certain instructions are executed or certain part of the codes are executed in a predefined sequence. So if you skip to different functions and the sequence count checker would not match, the coprocessor would also say something is wrong. Then it provides features for integer and Boolean validation, so comparing to register values or comparing a register value versus a magic constant. Once again, this is meant for hardening against fault injection attack, because sometimes you want to just compare two values while being sure that it's more hardened against normal software fault injection attacks. Lastly, it has one instruction for panic. So if a programmer sees something goes wrong, they can also ask the redundancy coprocessor to just panic right here and now, stop the course, stop the world, restart if needed. Now, to the boot process of the RP2350. The upper part of this graph is the low-level power on state machine. So that is all what's going on in hardware and can be seen as this in the Raspberry Pi 2350 documentation. The lower part is what we, by reading the source code, the documentation, and the binary code, kind of reverse engineered our understanding of the boot process. We will first start with starting the boot, which is meant to be run on core 0. So there's a check against whether are we on core 1 or 0. Then it will later on generate the boot random, and then checks two special boot vectors, the Paumann boot vector and the watchdog boot vector. The idea here is that there is a mechanism to use a different boot vector to just boot to a specified program counter and stack pointer value directly. Then the bootloader prepares for image boot and starts trying to boot from the different sources where firmware could be read or could be lying. The RAM, the one-time programmable memory, and the flash. And for each of this, if the secure boot chain is enabled or secure boot for the chip is enabled, for each of those, signature verification would happen at this stage. If the boot cell button was pressed or none of the valid firmware images were found, the bootloader would prepare for the so-called boot cell stage, which will drop us in one or two different bootloaders depending on the configuration, either a UART bootloader or a USB bootloader. Now, all of the little lightning emojis you see here is where our attacks were able, with fault injection, to bypass the guarantees of secure boot. In this talk later on, we will focus on these particular two attacks, but we will recap all others in a bit as well. Now, let's talk about how all of this plays together for creating the Raspberry Pi 2350 security challenge. First of all, a user or challenge participant will generate a public and private key pair. they would write a 128-bit secret value to the one-time programmable memory in row OXC08. It's the goal of the attacker to read out this secret. After this value is written, the SHA-256 value of the public key, which is known or which was generated, is written to the bootkey0 row in the OTP, and afterwards we would enable secure boot. At this point, only firmware which was signed with bootkey0 should be able to boot and run on the device. Then the chip is locked down. This includes mostly 4 operations. First, debug access is disabled. Second, all other boot key except bootkey0 are marked as invalid. The glitch detector is enabled and set to the highest sensitivity. And the OTP pages doing all of the security configurations are locked. This means that someone cannot afterwards write additional values to the OTP and maybe change some of the security configuration. After this is done, a custom firmware which was signed is run, which also removes the access to the secret which needs to be extracted from non-secure states. So this cannot be done completely in OTP configuration, which is why this is done once in firmware. And with all of that being set up, we have a secure chip which has a secure boot chain running a firmware. There is a secret stored in the one-time programmable memory, and as attacker, the goal is to extract the secret. And that brings us to our different attacks and how we did that and came to extract the secret. Now, we had 5 different attacks, right? Like 5 were mentioned in the post. The first one was an attack on the power-on state machine on the OTP. The second was forcing a reboot to a boot vector. The third was laser fold injection to change or to falsify signature verification. Then we had a one-time readout, a one-time programmable memory lock, double glitch via electromagnetic fault injection, and last, anti-fuse data extraction. In this presentation, we will focus on these 2 attacks, mostly because for the first one, the power-on state machine, there's an excellent Chaos Communication Congress talk. For the laser fold injection, there's an excellent blog post to read, and about the anti-fuse data extraction you will hear right after me. Okay, let's get started with forcing a vector boot. The context here is that the chip has the possibility to run a USB bootloader. And this USB bootloader runs in non-secure execution state, which makes a lot of sense, right? We're getting inputs from a user, so we want to be in the non-secure world. For some functionalities, it uses so-called boot ROM APIs, so it can call APIs calls, which which were implemented in the secure world. Before changing to those boot ROM APIs, the parameters are usually hardened against exploits and fault injection attacks alike. Now, the bootloader also implements the interaction with picotool, and there are a lot of different commands picotool can send. So this is a small command line utility to interact with the bootloader. And one of the commands which can be sent is the so-called reset command, which would reset the chip. And looking at the documentation and the code of picotool, there are multiple different ways to ask for a reset. The main command stays the same, but there are some magical combinations of the parameters which would indicate different boot types. There are a lot of different ones, like for instance, please reboot from RAM, because maybe as a programmer you just wrote temporary firmware into RAM. Now, one very special boot type in the documentation is the reboot type PCSP. The documentation says reboots to a specific program counter and stack pointer value, and it also explicitly notes that this is not allowed in the ARM non-security variant. So this part of the reboot, or this reboot API, can only be called under normal circumstances from the secure world. And we thought that's very interesting and started to dig a little bit deeper. So the reset command flow looks something like this. In the non-secure world, we receive the command and jump to the entry of the secure world with the reboot flag set. In the secure world, we start sanitizing the parameters which are coming in, and including the boot type parameter. So the OXD, which would be encoding reboot type PCSP, is shifted out of the flex variables, notifying or indicating this. And then the secure world will jump to the shared reset code, so to the boot ROM API, which then just verifies that the registers are matching, and then executes the requested boot type. So a lot of hardening happens before we go in the shared reboot command path between secure and non-secure world. And unfortunately, looking at this, we find a vulnerable instruction sequence here in the reboot RP. The highlighted instructions compare the flex register, register 5, with OX0D, and then has a branch not equal instruction. So it will branch to other reboot types as we're not equal. Now, if we are able to fault inject one of these instructions and trigger instruction skip, we would fall straight through into the branch which does the reboot type PCSP. So this was one excellent target for fault injection, and the attack strategy would be to load unsigned firmware in RAM, send a reboot command via USB, and glitch the critical instructions. To carry that out in practice, a couple of challenges needed to be overcome, like first, the attack code needed to be written itself, which would dump out the secret, feasibility of the glitch to be verified. We need to find a bypass for the glitch detector, find and calibrate the trigger, and bypassing the random instruction delay from the redundancy coprocessor. Here I want to especially highlight bypassing the glitch detector, which we were able to do. Here we have a little graph from our glitching attempts, and we can see in the text sometimes we trigger the glitch detector, but we also get successful glitches in profiling code. How can this happen? Well, we did some experimental profiling, and it turned out the glitch detector is calibrated to the normal sys clock of the RP2350 at 150 megahertz. Now, unfortunately, the bootloader runs from a different, slower clock. PLL is used to derive a clock from the USB connection or via the USB line. As a result, the sample points of the two flip-flops, which will sample the power domain with the glitch detector, shift too much apart, and an attacker could still inject a glitch just between those two sample points and successfully do fault injection attacks. The second attack I want to quickly highlight is the double fault on the OTP readout. And the context here is that at the beginning, in the early boot, all OTP configurations variables are available because the chip configures itself based on what's in there. And then only when preparing to going into the boot cell mode, so shortly before starting one of the two bootloaders, the boot ROM would execute code to apply the OTP logs as defined in the OTP memory. So if pages are locked and access should be revoked, it's done in this stage. And normally, a user can read non-locked OTP values. Here we have a screenshot where I read like kind of the critical security configuration from the chip. Locking down OTP codes, OTP pages look something like this in the boot ROM. We would twice jump to OTP advanced BL to S value, which will just get the configuration of whether a certain page should be locked or not. And we do this twice as hardening against fault injection, or the boot ROM does it twice. And then it uses HX assert equal to I, which is using the coprocessor to really assert that these two values are the same. If they are the same, the software log would be applied to the according page. Now, when we're looking at this OTP advanced BL to S value, there's one instruction which is pretty interesting. Don't mind the code, it does some things, but what it does as well is the value to be returned, the log bits, are first shifted to the left and then shifted to the right, effectively clearing all the upper bits. If we were to glitch and skip the instruction doing the shift to the right, we would have a software lag variable which looks something like this. Instead of having the most lowest bit sets, we only have the most high bit sets. And we experimentally verified that this kind of write, like if this value is returned and we write it to the OTP hardware, the OTP hardware peripheral would just ignore this write and nothing would be locked. So the page, despite it should have been locked, is still accessible by the user. So this gives the attack strategy here. We set up to boot into the boot cell mode. We bypass again the glitch detector. We glitch the critical instruction twice, and we do a readout of the secret just via the normal Pico tool. For this attack, bypassing the glitch detector was a little bit different. While the clock was also slower here, we could use also another approach, because glitch detectors measure at specific physical locations on the chip, and with EMFI we can just localize. So we tested around with the EMFI probe, and we see here a small graph. The brighter the color, the better it is, the more successes we have while trying glitching. And we see here at white like one point which is extremely good to bypass the glitch detector. Okay, these were the small attacks I wanted to highlight. Let's briefly look into mitigations and errata. So 4 of these attacks received an errata, except of the anti-fuse data extractions, as I think that was a bit out of scope originally of the challenge, but it was still recognized. And for errata 20 and 21, there were also software mitigations and workarounds provided. So that's exactly the 2 attacks we talked about. Now, 1.5 weeks ago, Raspberry released the new revision of the chip publicly, the A4 revision, and that fixes all of this in hardware, or all of this 4 erratas. So now the new Raspberry Pi 2350 A4 chip is secured against the attacks we looked here. Let's wrap up and look at the lessons learned. I think one bit to take away is the importance to also have fault models for pre-boot attacks. So before code runs, hardware is also vulnerable to fault attacks. It's not enough to only have models thinking about instruction skips or similar. We've seen it here, but we also saw other attacks in the past which would bring up debug accesses, for instance, again, or unlock locked flash chips. We also discuss a little bit the effectiveness of hardware mitigations. The glitch detector and the redundancy coprocessor are both great hardware mitigations in making our lives as attacker harder. The cost of an attack rises, but we're still able to bypass them eventually. Then there is definitely some danger of complicated boot paths, right? Like most of the attacks we saw here are based on the fact that the bootloader just has a lot of different functionality and can do a lot of different things. And it's really difficult to harden all of these different aspects. And the last takeaway, which is shown up by other work as well in the recent years, is that laser fold injection, which was traditionally more of an expensive technique, becomes accessible. Like one can build relatively cheap laser fold injection setups for below $1,000 by now. Okay, that concludes my talk. The artifact and paper is available over there. And usually I would now have like just a 3 bullet point of the main highlights of the talks, but I think for this one I want to break this tradition and just say security through transparency is amazing. Like what Raspberry did there is, in my opinion, great. We can look at their chips in a safe setting. They can revise based on the attacks we find, and overall it just leads to a more secure ecosystem of chips. Thank you.